Hey, physics students. This is still Chapter 11. There was a figure missing from this example in the guided notes, so I went back and dug it up, and now I'm going to work it. Let's see here. My tablet over here. Now, where is it? Here it is. Okay, so it's a floating raft. It's made out of wood. First of all, you're supposed to determine whether the raft floats in water. Well, in that table back at the beginning of this chapter, we found that the density of wood is equal to 550 kilograms per cubic meter. Anything that has a density less than 1,000 kilograms per cubic meter will float in water because the density is less than the density of water. So we're supposed to determine how much of this raft is below the surface. They're calling that height h here. In the picture, they're telling us that the raft is 0.3 meters thick, and it's 4 meters by 4 meters. Okay, so if it's balancing or floating, that means that the buoyant force, which I think they use FB, I'm going to use BF, best friend. Buoyant force can be your best friend if you're stuck and floating in the ocean. And mg is downward. These are the two vertical forces that are canceling out to get the raft to float. Now, the buoyant force depends on h, depends on how much of the raft is below the water. And in fact, the equation I'm going to use here is that m is equal to rho times v, the volume. So the buoyancy force is the weight of the water, according to Archimedes' principle. It's the weight of the water that's displaced, and that's equal to mg. So the buoyancy force is equal to the density of water. I'm going to call that H2O because water and wood start with the same letter. The density times the volume. Now the volume is going to be the area, 16 meters squared, 4 times 4, times how much is under the water, which is h. Okay, also times g, because this is the mass of the water displaced. So I'd multiply that by g to get the weight of the water displaced. That's going to equal mg, the mass of the wood. The mass of the wood is the density of wood times the volume of the wood. Well, that's equal to 16 meters squared times 0.3 meters. And that would be also times g. Well, a bunch of stuff cancels here. 16 meters squared cancels. The g cancels. The density of water is 1,000 kilograms per cubic meter. H is what I'm looking for. The density of wood is 550 kilograms per cubic meter, according to that table. And this would be 0.3 meters. So that's equal to, simple enough, 550 divided by 1,000 is 0.55 times 0.3. 0.55 times 0.3. 0.165 meters. So that's how much of it sinks down. So that's that problem. Now, let's go look at couple of the homework problems for this section. Chapter 11. Since I got a little more time here, I'll make a couple comments. An airplane wing has an effective surface area of that is generating a lift force. In level flight, the airspeed over the top of the wings is 52 meters per second, while the speed below the wings is 35 meters per second. What's the weight of the plane? Okay, I'm not going to work this out in detail. I'm just going to look at the equations that we're going to use for this problem. This is 1172. The first equation I'm going to use, since the top of the airplane wing is essentially at the same height as the bottom of the airplane wing. Isn't that wonderful? Where is my problem? This is my scrap paper. Since the top of the airplane wing, Y1 and Y2 are the same, we'll let P1 and V1 be the top of the airplane. We'll let it be the bottom of the airplane. Plus 1/2 rho V2 squared. We'll let, doesn't matter which, we'll let this be the bottom. And this the top. So now the pressure difference between the top and the bottom is what's causing this airplane to have lift. The pressure below the wing is going to be greater than the pressure above the wing. So I'm going to bring the pressure on the top of the wing over to the right hand side, and I'm going to bring the pressure, the velocity at the bottom of the wing over to this side of the equation. Oh, you can't see my tablet. Let's get it out there so you can see what I'm doing. Okay, so there's Bernoulli's equation with Y1 and Y2 being the same. I rearranged to get the pressure difference on the right-hand side. And then I'm going to, the lift force, which I'll call F lift, is equal to the pressure difference, P2 minus P1, times the area. And if the plane is flying level, that's equal to the weight, mg. So I just plug in my values for V1, which is the top of the wing, which is 52.52, and the velocity below the wing, which is 35. Then you need the density of air. That's in your book somewhere. It's about 1 kilogram per cubic meter. So this row here is the density of air. It's about 1 kilogram per cubic meter. If you want to get exactly their answer, you probably are going to might have to use a closer value given in the book. All right, that's how that problem goes. Let's look at this one. Okay, physics students, let's look at problem 68, 1168. Here's how that problem would go. There's the ship, 2.2 meters below the surface. You have a hole. So this is just like the example. This is 1168. This is just like the example of a hole in a tank that's a certain distance below the surface. And we found V is equal to the square root of 2GH in the notes. And so you would find the velocity with that. And then the rate at which volume flows through a hole is equal to the velocity of the fluid times the area of the hole. And that would give you units of meters per second times meters squared. That'd be meters cubed per second. Yes, that's the right units. So those are the formulas you'd use for that. 1140. This is sort of like the floating raft problem. I think I'll leave that for you. Here's 1144. Here's how that problem would go. When I weigh it in air, we ignore the buoyancy force of air, then the reading on the scale would just be mg. M is equal to rho times V. That's a formula that I'm using routinely here. So the 8.57, which is the weight, no, 20.3. I was doing a different numerical example when I was working that out. 20.3 in my case would be equal to the density of the paper weight, which I'm just calling rho, times the volume of the paper weight times G. And then when they weigh it in water, the problem I was working here was they had a number 5.39. Here they got 14.4 newtons. That's equal to the weight in air minus the buoyancy force of the water. That's the density of water times the volume times G. So it's equal to the difference between those two. So now, if I take, where I got rho VG here, I'm going to substitute 20.3. So the second equation becomes 14.4 equals 20.3 minus the density of water times the volume of the paperweight times G. I do know the density of water. Okay. So what do I do now? I'm going to take this 14.4 and bring it over to the right-hand side, and I'm going to take this and bring it to the left-hand side. So the density of water times the volume of the paperweight times G is equal to 20.3 minus 14.4 newtons. And you know the density of water, it's 1,000 kilograms per cubic meter. And you know G, so you can find V, the volume of the paperweight. All right, that was kind of fun. I'll leave that one for you.